In the previous session, I gave you a pretty strong hint on how to simplify the Schrodinger equation of the previous session, and here's the hint. Now, from the previous chapter, chapter 7 on angular momentum, if you've been studying it closely, you will recognize this term here is the polar angle theta phi operator, the operator and the function of those two angles, polar angles, and that's the expression for L hat squared, the angular momentum, L. So L squared is this, and this also comes out of vector calculus. It's the r theta, well in this case theta phi, equivalent of the angular momentum operators expressed in terms of the Cartesian coordinate system x, y, z. So you'll understand why I consider it. I'm getting all these links and references to classical mechanics, so I will teach a vector calculus mini course. All right. So, but this is very similar to two of the terms. You've got this term plus, so the theta dependent term and a phi dependent term, or there's a theta as well here. But this features in the Schrodinger equation of the previous session. So it gives a hint. Well, instead of this stuff, plug in the L hat squared into that Schrodinger equation. Now there's the Schrodinger equation had an r squared underneath here, so you can rewrite the Schrodinger equation of the previous session into so you can rewrite it in this form. Okay, so the polar angles term sort of, well, doesn't disappear, but just gets rewritten, and so all this gets replaced by L hat squared, right? And you have to modify things a bit because this doesn't have an r squared underneath, so you put it here to make it the same as the Schrodinger equation before, right? Okay, now you start looking at this per se, and you start noticing some really interesting things about it, and you can make deductions from those observations. For example, have a look at this thing. Now, so all this is h bar, right? It's h hat. H bar, Planck's constant. It's interesting the way the brain works. Right? It just gets set in grooves. You go down a verbal groove. Here h, you automatically say bar. No, I want to say h hat. Right? I'm talking about the Hamiltonian operator, not Planck's constant. So h hat. This is h hat. Okay. Now, if I multiply, so it's an operator, right? Now, if I put another operator to the right of it, say L squared. Can you see that ah L squared will be the same as putting this operator on the left side, so L squared h? And if that's the case, then the commutator of h hat L hat squared is 0. In other words, these two operators commute. And remember from earlier theory, if two operators commute, they are compatible, and as well they have eigenfunctions that are the same set of eigenfunctions, right? So if the Hamiltonian h hat and L squared, or L hat squared, if those two commute, if they are 0, if this commutator here is 0, then these eigenfunctions here, because they're the eigenfunctions of h hat, right? Those eigenfunctions will also be the eigenfunctions for L hat squared. Wow. Okay. All right. So let's. Now I've been saying if a lot, so let's actually show that this is the case, that this commutator is 0. In other words, if I put the L squared on the left or on the right here, the effect's the same. Now why is that? Well, look at the form of L squareds. Have a look at it here. It's got nothing to do with R, right? It's just all thetas and phis. Whereas this term here is just all R's, right? So the R and the thetas, they're nothing to do with each other. So if I put L squared here on the left, the thetas and phis have nothing to do with the R's. I could just as easily put the L squared on the right of this. Okay? Now L squared, if they commute obviously because they're the same thing. V is just a scalar, right? So V L squared is the same as L squared V, right? So can you see that putting L squared either on the left or the right of the H hat operator, it's the same. Works out the same because of the independence of the R and the polar angles. Hope that's obvious, right? Okay, well, I hope you follow that reasoning. So that means that the Hamiltonian operator, this H hat, and L hat squared, this is your angular momentum operator. You had two main ones, remember? The other one was the Z component of the angular momentum, so LZ hat. And you know from theory of previous chapter, you know that these two commute. They are compatible, right? You can measure both of them accurately simultaneously. So these two commute. Therefore they have the same eigenfunctions. Can you remember what they were? What are the eigenfunctions of the angular momentum or menta operators? L squared and LZ. Well, the spherical harmonics, the y's, right? Here, right? The YLM. Okay, so why, if you form the commutator of the Hamiltonian, so H hat and LZ hat, it says here that also commutes. Well, why is that? Well, because these two are compatible, right? They commute. But this commutes with a Hamiltonian. So, therefore, this should commute with a Hamiltonian. Is that right? Is that obvious? You need to think about that. There's a question for you. Is this kind of thing transitive? So, let me put that in the abstract. So, if two operators, A and B, if they commute, and if A and C, so the third operator, if A and C, those two operators commute, does it imply that B and C also commute? So, need to think about that. I guess so. It's just straight out of the text. So that commutes with that. We just talked about that, and we know that L squared and LZ commute. So does that mean? Or could I use the same? Hold on, maybe I could do it a different way. Maybe I could prove that this commutes simply by the same logic and put my LZ left and I'll do it that way. I'll go around the problem. If you can't solve a problem head on, then just go around it. Okay. All right. So I'm going to use the same logic as showing that this one is that the commutator is 0 by doing the same type of reasoning. I'm going to put the LZ on the left here and the right here. Now because LZ, its formula has nothing to do with R. I think it's just dBd phi or something. It's very simple. That's the reason why we chose the Z component rather than the Lx or Ly. Okay. Anyway, so the L dBd phi, the differential form of this, has nothing to do with the R's. Okay? So this is also true. You know, the commutator of the Hamiltonian LZ is 0. Okay. Alright. Now, further deductions. You may also remember some theory that if some operator commutes with the Hamiltonian, then the observable corresponding to that operator is conserved. That means it does not change with time. Now, in the quantum mechanical context, if some operator commutes with the Hamiltonian, the expectation value of that operator is conserved, meaning it does not change with time. So if you differentiate that expectation value, you'll get 0, right? It's conserved. So that means that L squared and the Z component of L are conserved, right? So conservation of angular momentum, if you like, right? And so L squared and LZ are conserved, and H hat, you know, the Hamiltonian, L hat squared and LZ hat, all three of them have the same set of eigenstates. Okay? Because the commutator is 0 with the Hamiltonian, this commutator is 0 with the Hamiltonian. So these all three have the same eigenstates, same set of eigenstates. Alright, now what are the eigenstates of the angular momentum? Well, I was just saying before, they're the spherical harmonics, right? We did that in the previous chapter. So the eigenfunctions of this operator and this operator are this, and for the Hamiltonian H as well. Alright, now it's not quite as